So this formula will calculate how many newtons a charged particle will feel if it moves into a magnetic field at a certain speed. You'll see by this formula that the force is directly proportional to the charge of the particle, the velocity of the particle, and the magnetic field is directly proportional to all three of those. Okay, so I just want to start getting used to this formula here. So do part A first. So part A is a proton, and you may need to look up some things. So you have to go back to the useful values document that's posted within this unit to get the charge of a proton and to get the mass of a proton. So I have those memorized actually, so I'll just write them down, but you might have to look them up for homework. So the charge of a proton is 1.60 times 10 to the negative 19 coulombs. And the mass of a proton is 1.67 times 10 to the negative 27 kilograms. I hope. Now, this particle is going to be fired with a given velocity that's written in the question. So that's 2.0 times 10 to the 5 meters per second. And the strength of the magnetic field is also given, 3.0 times 10 to the negative 4 Teslas. In terms of directions, the velocity, it's told that it's into the page. And the magnetic field, it's told that it's left. So I'll just draw a little picture of that. So the magnetic field is left. So it's going to kind of fill this whole space here. The magnetic field is to the left. And the particle, the velocity, is into the page. So you have some random particle here, and it's moving into the page. So it's hard for me to actually draw that. I'll just write it out. Now we're using right-hand rule number 3 here. I forgot to get the picture of that, but the index finger needs to be at the velocity of the charge. The middle finger needs to be the magnetic field, and your thumb will end up pointing in the force. Okay. I want to talk a little bit about the numbers listed out here. The velocity you'll see is 10 to the 5, which is acceptable. So what's not acceptable is anything higher than the speed of light, for sure, which is 3 times 10 to the 8. And we also do not want anything even within like 10% of the speed of light. We don't even want it to go that fast. So 10 to the exponent 7 meters per second, that's kind of going too fast for our liking. When you get faster than that, when you get too close to the speed of light, you start having things called relativistic effects, which really screw things up. So we normally deal with that in the very last unit of the course. We probably actually won't have time to get to that unit, but for this particular unit, we don't want to deal with that. So we got to make sure our speeds stay like 10 to the 6 or lower for meters per second. And in terms of the magnetic field, it's given as 10 to the negative 4 Tesla, which is about 10 times stronger than Earth's magnetic field, it's pretty decent. So like when we do these experiments, we don't want Earth's magnetic field to be a big influence on what goes on. So the magnetic field we use in our experiments need to be kind of significantly stronger to kind of dominate the behavior of these particles. All right, anyways, let's calculate this. So I'll use this formula. Now, I'm going to be a little bit lazy here. This is the unit where I make kind of an exception. where instead of writing vector arrows and magnitude bars for all of those terms, because that's a lot, I'm going to take a little shortcut and just write the letters with no vector arrows and with no magnitude bars. This represents the magnitude of the force. And in terms of sine of theta, the angle is 90 degrees. So the angle is between the velocity and the magnetic field. So if the velocity is going into the page and the magnetic field is going left, they make a 90-degree angle with each other. So it is just sine of 90 degrees, which is nice because sine of 90 degrees is 1. So anything times 1 is itself, so we can kind of cross it out of our equation. Okay, so I'm basically multiplying QVB. Okay, I'm not going to write it all out. I'm just going to, the values are listed on the left there, so I'm just going to go on to a calculator here and get that solved. So this is my process. I'm going to do 1.6 for the charge times 2 for the velocity times 3 for the magnetic field, and then come up with 9.6, which I love because that's between 1 and 10. So it's already set up for scientific notation. And I'm going to do the scientific notation kind of in my head because I don't exactly like typing out times 10 to the this, times 10 to the that a whole bunch of times in my calculator. So I'm going to use my exponent laws. So my power of 10, it'll be, so 10 to the negative 19, and then 10 to the 5 for velocity. So add those together, that makes negative 14. And then 10 to the negative 4 from the magnetic field. So add that to it, makes 10 to the negative 18. And the units will be in newtons because everything I've listed out is in SI units. Now, what about the direction? So that gives the magnitude of the force. What about the direction of the force? That's got to be obtained by right-hand rule number 3. So I'll stick my index finger into the page. That's the velocity. I'll twist my wrist so that my middle finger points to the left for the magnetic field, and my thumb ends up pointing up. That'll be the force for part A for a proton. I'll put an A there that only applies to A. All right. For B, C, and D, I'm actually not going to calculate the final values. We could, but that takes a lot of time, and I'm just going to talk conceptually about what the answers should be like. So B, what if we do the same question, but it's not a proton, it's an electron? Well, one difference is that since the charge is negative, the direction of the resulting force will end up being the opposite direction. So it'll be an answer that's down. Secondly, an electron has the exact same charge as a proton, it's just negative. So the magnitude will be the same because the Q value is the same. So the force on an electron will be the exact same. It's just the opposite direction. Now, the accelerations will be different. Again, I'm not going to calculate it out, but the accelerations will be net force divided by the mass. So I take my force divided by the mass of the proton. Okay, I'll do it for the proton. So I'll take that number for the force divided by the 1.67. That gives me 5.7. And that'll be times 10 to the, so exponent laws here, negative 18 minus negative 27 gives me 10 to the 9 meters per second squared. Okay, so that'll be the acceleration of the proton. By the way, that does not violate the speed of light because that's the acceleration. It's not the speed of the proton. What about the acceleration of the electron then? It's going to be way more. I won't calculate it this time, but it will be much higher due to a much lower mass. It's a lot less massive than the proton. Okay, C, what about a neutron? Well, a neutron, the force will actually just be 0 because the charge of a neutron is 0. The neutrons have no charge. So that one's the simplest one. And then finally, an alpha particle, which is a helium nucleus, which contains 2 protons and 2 neutrons. So what we have to understand is that alpha particle is double the charge compared to a proton. And quadruple the mass because it has neutrons in it. And a neutron and a proton have approximately the same mass. To round it to 3 significant digits, it's the same, 1.67 times 10 to the negative 27. So, but they don't have any charge. So an alpha particle has double the charge, so double the Q, and quadruple the mass. So how will this affect force? How will this affect acceleration? Therefore, the force on an alpha particle, since the charge is doubled, that's just going to double the answer. So I'll say the force will be double compared to our answer to part A. And how about the acceleration? The acceleration is actually going to be half compared to our answer to A. So we have double the force, so it doubles the acceleration. However, we quadruple the mass, so the acceleration goes down by a factor of 1/4. Combining those two effects, it ends up being reduced by a factor of 1/2.